ladies and gentlemen. Let me present the results of work performed in Dnipropetrovsk National University in collaboration with Institute of Physics of National Academy of Science of Ukraine. In first, a little introduction to synthetic opals. These structures are made of monodisperse silica dioxide globules, and the diameter of globules can be varied from 100 to 1,000 nanometers, and depending on method of synthesis of globules. These structures can be packed into two usual crystal structures, face center cubic lattice, or hexagonal close packing structure. But in work of Dergachov et.al., it was shown that FCC lattice is more preferable, more stable, more probable. I should say that many terms from solid-state physics are used to describe properties of such systems. But these systems, I mean synthetic opals, are not crystals as we think about it usually. It's not it's not crystal, but periodic structure. These structures are periodical, and optical properties of opals are due to Bragg's diffraction in periodic structure. And in this case, we can see Bragg diffraction of light, visible light, first of all. In contrary to classical crystals, we can see X-ray diffraction. And in the right-hand corner, the lower equation. And as I have just said, classical indexes, crystallographic crystal indexes are used. Bragg diffraction results in forming energy gaps in the photon spectrum of such systems. In opal, the gap in photon spectrum is in some spatial directions, not in all spatial directions. And this is why the structure are attributed to photonic crystals, but we must keep in mind that not band in all spatial direction. And this band in energy spectrum called stop band in different directions. There is no band. Stop band is a term which are widely used in Russian literature. In English literature, pseudo gap. In optical spectra, we can see the appearance of this stop band. And these are typical reflection or transmission spectra. And for example, in our initial opals, in the visible region, we can see two non-transmission band. I don't say absorption band, because it's not absorption in classical sense. And these bands are corresponded to reflection bands. And here you can see indexes which correspond to planes. The reflection peak or non-transmission peak are determined by the Bragg diffractions law, where epsilon effective is the effective dielectric constant, which are determined by dielectric constant of silica dioxide, and other components which can be embedded into opal structure. Synthetic opal consisted of regular structure of cavities or channel in the structure, and this porous may be filled with compound that you want to use. There are some trends in the fabricating new nanocomposites. First of all, this is filling with active dielectrics. Here you can see a number of dielectrics and effect. Many new effects can be observed in such structures. Modification of structure and properties of embedded substances, enhancement of spontaneous Raman scattering, and other linear and nonlinear optical phenomena. Another trend, filling with semiconductor, and in this case, usually luminescent properties are studied. First of all, the inhibition effect near the stop band, and enhancement radiation nearby the edges of stop band. I mean, nearby this region, we might have enhancement of spontaneous radiation, and in this region we have inhibition or suppression of spontaneous radiation. Synthetic opals are not of a great interest themselves. They are very promising matrices for creating nanocomposites. In our case, we choose nonlinear materials. As you know, KDP is classical nonlinear optical materials, and lithium tetraborate is very popular nonlinear optical materials. This is characteristics of some of the characteristics of these materials. And this is images of the surface of our opals. We have studied opals with average diameter of global. This figure for opal of D with 270 nanometer, and an average linear size, of course, up to 70 nanometer. And these pores we want to fill with nonlinear materials. In what way? There are some procedures, for example, soaking, laser ablation, and synthesis, chemical synthesis, into pores of such systems. We prefer soaking. Like you put a sponge into water soap solution, we put our initial sample into solution which contain compound we want to embed. As you know, KDP is water soluble. Because of room temperature, we obtained supersaturated KDP water solution, and by multiple soaking we can obtain our nanocomposite. After this, we dry our opal in order to extract water. in air at room temperature and at at higher temperature at 390 Kelvin. In case of LB4, the situation is difficult. This crystal is not soluble in water, but to use acid is very dangerous. But in this case, we obtain fine dispersive polycrystalline LB4 powder, place our opal on the substrate, and then place powder on the top side. Or in another case, on the substrate, in first powder and then opal. And we heat the system to the temperature slightly higher than melting temperature. And then the system was held during 5 minutes or half an hour. Half an hour, 25 minutes. And then system was cooled down room temperature with an average cooling rate of 3 Kelvin per minute. So, experimental setup was traditional setup. A laser spectrometer was based on double monochromator DFS 12. All traditional scattering geometries were used, right angle scattering, back scattering, forward scattering, you see. And sources of optical excitation were as following: light emitting diode at 400 nanometers, laser diode, DPSS laser, and incandescent lamp. The latter was used for measuring reflection of transmission spectrum, as you see. Now I want to separate results obtained for opal KDP and opal LB4. First of all, we have to obtain provement that something changes, take place in our system. Unfortunately, by now we haven't performed X-ray measurements. There were some technical difficulties. But owing to the fact that diameter of globules is close to visible light wavelengths, we can use transmission and reflection technique to determine changes. And in our case, dotted line is corresponded to initial opal, but solid line 2 and 3, this is a transmission spectra after 1 infiltration cycle or 2 infiltration cycles. As you can see, there is no essential shift transmission minimum. Why? Maybe it testifies the small quantity of KDP in topology. But there is another features which point out to changes. The band gap, the band which corresponds to stop band, becomes narrow. It may testify that we have changes optical contrast. Optical contrast is the ratio between refraction index of silica dioxide and refraction index of KDP. As you can see, they are very close. by embedding even small quantity of KDP, we decrease an optical contrast. As you know, for example, Yarev and Yuh, for electromagnetic waves in periodic structure, the width of the stop band is determined, is proportional to the delta n, and where delta n is expressed by the following expression. So I think we have obtained a provement that we have system opal KTP. Now, Raman spectrum. Raman spectrum is necessary to say something about structure, first of all. But what you can see, the Raman spectrum of our opal system under green excitation is unexpected, is very unexpected. In the left in the right hand corner, upper corner, you can see Raman spectrum at room temperatures for KDP. They are not similar. What is the nature? What does it mean? What is the nature of this radiation? Maybe luminescence. Luminescence of what? Luminescence of impurity center. We can assume that impurities. But in this case, the transmission nearby the laser line excitation in our transmission spectrum must be low. Must be low. But in our case, we don't observe this. Well, maybe it's Raman scattering of amorphous state. Maybe. But we measured anti-Stokes spot, and in this figure you can see simulation of anti-Stokes spot. Here. You can see that anti-Stokes spot in this case must be much higher than that we have observed. What is the reason? Maybe these other processes. I must say that we have a nonlinear optical system. In order to clear up the nature, we change the excitation wavelengths, ultraviolet excitation. In the case of luminescence, we must obtain the most powerful signal, but no more. This very weak radiation. And now we can compare with photoluminescence for KGP and KPO3 under ultraviolet radiation. There is no more. This spectra is not like. And now, in the left-hand corner, you can see two spectra under green and violet excitation, and you can see that are very close to each other. And the second peculiarities, the increase of intensity is corresponded to the edge of stop band. And I want to say that near by the stop band, the density of optical states is like to the density of states in classical crystal nearby the Van Hoff singularities. Nearby the stop band, the density of optical state is much higher than in other regions. This is why we assume nonlinear optical processes, spontaneous parametric down conversion. The reason for it is as follows. We have obtained similar behavior in other systems with other nonlinear materials, as presented above. In our case, we have especially non-uniform media, and the momentum conversation law must additional part with a reciprocal lattice vector. Now, about opal LB4 systems. We have failed in obtaining very good transmission spectra of opal LB4 systems because of the samples after infiltration cycle becomes very transparent. And there was no transmission or reflection band connected with photonic band structure, band gap structure. You can see, but it's very unexpected because the refraction index are quite different, quite different. I present the mean value of refraction index, estimated value, you see. We use a transparent optical microscope to obtain the images of samples, surfaces, and as you can see, they are very transparent. They are very transparent. We measured Raman spectra. This is Raman spectra for sample which was held at temperature of melting or soaking time. 5 minutes, the minimum time. The highest spectrum, LB for crystal Raman spectrum. As you can see, some lines are shifted. We may say that some bands are shifted, and we may connect it with side effects. But in the spectra, there is a band which very coincide with a band in a Raman spectrum of alpha quartz. 5 minutes. Okay. And further, we measured spectra for samples obtained at longer soaking time. And in this case, the spectrum which may be assigned to LB4 vibration, LB4 Raman spectrum, is vanished. And only part which are connected, which are assigned to Raman spectrum of alpha quartz, is present. You can see the white band. This band are corresponded to bands of initial opal. Globules which globules in opal structure is an amorphous state. As you can see. And so we, in the presence of lithium tetraborate powder, at temperature much lower than usual temperature, we can obtain alpha crystalline quartz in this case. Conclusions: infiltration of synthetic opals resulting in increasing transmission, and in narrow non-transmission band. Its secondary emission may be connected with parametric down conversion, and crystalline quartz state is formed in opal matrices by silicon into lithium tetraborate melt during longer than 5 minutes. This work was supported by Ukrainian-Russian project. Thank you for your attention. Sorry for my English.
Thank you very much for the nice talk. The talk is open for discussions.
How can you clarify the crystallization process? The reason.
We repeat in our infiltration cycle, as for LB4, we repeat the process like process that was held in the usual condition. By cooling, what do you mean? By cooling our sample, the melt was cooled, and you see there are some ways of forming state after cooling: amorphous state and crystalline state, solid crystalline state. But in this case and in other systems, the poster presentation will be tomorrow. We can, by using Raman spectroscopy technique, crystalline the phase.
This is somehow a related question. Is it very important to control the direction of the wave vector with respect to the crystalline plane? But if I'm right, in your sample you have powder, so that means that you have all the orientation possible.
Oh yeah, all orientation.
What are the size of the grains? Because you have not a perfect crystal. So you have there are a lot of grains, small grains, and so what is the size of the crystals?
Do you mean that obtained optical phenomena is due to defects on not defects?
Maybe not. No. I mean the primary area. There might be some second effect due to the boundaries, but just to have an idea, it would be very interesting to really tune the angle of the wave vector with respect to the crystalline plane. In that case, it would
we changed.
A very large crystal. So, what is the size of the monocrystal?
In our case, we have, I think, another system. It's not like two single crystal, first of all. On the second hand, we have measured spectra in some different geometries. And as for parametric down conversion, we have, but not for opal KDP system, we have measured angular dependencies of radiation after our sample. That's all.
So we have time for one more short question. So if not, let's take the speaker.